In this video, we're going to look at natural exponential functions. So here, the base of our exponential is e, which is a near rational number, which is approximated by about 2.72. And so if we look at our compound interest formula, and if we just use the fact that e is 1 plus 1 over n to the nth power, as n goes to infinity, this becomes closer and closer to e. Okay, so that's how that's defined. And so what I want to do is see, it looks similar to what's going on in my compound interest. Okay, and where n is how often I get to add interest into my account, the time segments that my interest is going in. Okay, so if I take, and just bear with me, I'm going to divide both by r. This part you're not going to need to know for your homework. I'm just showing you where this comes from. Then I'm going to let x equal n over r. Okay, that's close, isn't it? It's the reciprocal. So then this would go to 1 plus 1 over x. And then I have an n over r here. And then this would be, I still have that TR. Okay, now that looks right here a whole lot like what I have right here. So as we have our n, or the number of times that we're compounding, if that's going towards infinity, then this is going towards e. So then we would still have the p, and this is tr. All right, and then it's usually just written with my r and then t. So the amount, after a certain amount of time compounding continuously, then we would get this new formula for continuously compounding interest. Okay, so as n goes towards infinity, this is going towards infinity, so x is going towards infinity, and then we can replace 1 over 1 plus x to the x with e if our x is going towards infinity. Okay, so you don't need to kind of understand how to come up with that formula, but you do need to be able to use it. And then I really want you to think, just to understand e, that is what happens when we're describing growth, but instead of, it just happening where the growth kind of just after 1 year doubles. After 2 years, that doubles again. After 3 years, it doubles again. But the continuously growing, where it's not just compounded at a certain particular time and then doubles. But like if we're describing something like tree growth, it's happening at all times, day and night. So this compounding continuously is a better way of representing growth in nature. Okay, so that's kind of where that natural exponential log, why that's called the natural log. So let's go ahead and see what a picture of this would look like. Okay, so I would have my same y-intercept at 0, 1. Y is e to the x. 1, 0, 1, 2. So this would be e to the 0, which is 1, e to the 1, which is e. So that's about 2.72. I'm going to put that about here. And this would be e squared, which is about 7.4. That would be up off our graph. Okay, so, and then here this would be 1 over e. So it still has that same shape of a classic exponential, our horizontal asymptote here, is at y equals 0. All right, so the applications tend to be from nature. So this idea of continuously compounding interest, it's an important idea, the idea of it, but it actually isn't something that happens in the real world. With credit cards, the bills do kind of rack up, what you owe in interest can rack up because those are compounded daily, but we don't actually have any examples where interest is compounded continuously. Okay, but if it were, that would be your formula. But the base, the understanding that idea of growth and the rate, that does help us understand a lot of examples in nature. So for example, we have the amount of drug in a patient remaining in the bloodstream T hours after administered. It's gonna be diluting and like exiting out of the bloodstream continuously, right? A tiny bit at a time, but continuously. So this idea of the E as our base really makes sense in this situation. Okay, so using that formula, the question is how much of the drug remains in the patient's bloodstream after 2 hours. So our T in this case is 2. So we're going to find D of 2. So it would be 50 times e to the negative 0.2 times 2. 50 e to the negative 0.4. And that is approximately 33.52. And our units here are milligrams. All right, another example that is extremely useful is modeling population growth, or virus growth. So the population of a certain bird species after 2 years is given by this formula: 5,600 divided by 0.5 plus 27.5 e to the negative 0.44 t. Okay, so the first question is find the initial bird population. The key here is initial. That is letting us know that it's the beginning when t is 0. Okay, so what we're actually being asked to find there is the number of birds when t is 0. So let's just plug that in. So 5,600 divided by 0.5 plus 27.5 e to the negative 0.044 times 0, and then that just simplifies 0.5, 27.5, that would just be e to the 0, which is 1. So it would be 27.5 times 1 plus that 0.5, so it would be divided by 28, which is 200. Okay, so that's the initial number of birds. Now in B, as time goes on, what size does the population approach? So just like we won't have situations where your bank is just continuously giving you interest, compounding continuously, population growth, it can have an exponential start, but at some point it's going to run, we're going to run out of resources. And so it's going to be described with this, what's called a logistic curve. Okay, so what we can do is just look at our graph here. If you just plug this into Desmos, all right, and just type all that in and then graph that. Okay, remember that our y-intercept was at 200, so we're going to have to really zoom way out. Okay, and as time goes on, so we're looking at a t of infinity, right? Or like time has to pass for a long time, and then we can start looking at what's happening with our output. So it's looking like it's going towards 11,200. So if we had a y-intercept of 200, and then it was going up, and that horizontal asymptote was at 11,200. So as time goes on, what is the size of the population approach? And that is approaching 11,200 birds if the initial population was 200 birds. And we can kind of think about this in terms of our formula. So if we are taking 5,600 and dividing by this 27.5 e to the negative 0, let's get my graph out of the way, 0.044t. Okay, so that is a negative exponent. So that would mean that I can do the reciprocal of e to the positive power. So this could simplify to 5,600 divided by 0.5 plus 27.5 divided by e to the positive power, 0.044t. So as time goes on, so as t is going towards infinity, what's happening here? We're dividing by a bigger and bigger and bigger and bigger thing. And kind of think of this in terms of money. If we had $27.50 and we're dividing it, we're sharing it between more and more and more and more people, what each of us gets, that goes towards 0. So that becomes less and less and less. And what we end up getting closer and closer to is just 5,600 divided by 0.05, which is 11,200.